ground fault detection options include several methods. Firstly, consider a ground fault circuit interrupter, known as a GFCI. Note that a GFCI requires a grounded neutral and is not suitable for ungrounded systems. Secondly, explore the use of a ground fault relay, also known as a GFR. A GFR can be used for ungrounded systems, as it monitors the current in the neutral or ground wire. When the current exceeds a predefined value, the relay trips the circuit. Thirdly, examine a ground resistance monitor, referred to as a GRM. A GRM measures the resistance between the equipment frame and the ground. If the resistance exceeds a predetermined value, the monitor triggers an alarm or shuts down the equipment. Fourthly, look into using a Rogowski coil and relay. A Rogowski coil is a non-invasive current sensor. The coil is placed around the supply conductors and connected to a relay. It detects any current flow in the ground wire and trips the relay. Fifthly, you could use a portable ground fault indicator. This is a handheld device that measures the voltage between the equipment frame and the ground. It indicates if the ground connection is intact or compromised. For an ungrounded 480-volt service, consider using a ground fault relay, GFR. GFR are specifically designed for floating systems and can provide reliable ground fault detection. Regarding installation, the GFR should be installed in the main panel of the mobile lift. The neutral wire from the supply cord should be connected to the neutral or ground terminal of the GFR. The ground wire from the supply cord should be connected to the ground terminal of the GFR. The GFR should be set to trip at a current value appropriate for the system. It is important to test the ground fault detection system regularly to ensure proper operation. Additionally, the equipment should be inspected periodically to ensure that all connections are tight and secure. When evaluating ground fault protection, remember that ungrounded systems operate differently from grounded systems. In a grounded system, a ground fault creates a direct path for current to flow back to the source, causing a large current that trips a circuit breaker or fuse. This rapid response is due to the low impedance path provided by the ground wire. However, in an ungrounded system, there is no intentional connection to ground. A single ground fault will not immediately trip a breaker because there is no complete circuit for the fault current to return to the source. Instead, the voltage of the entire system will shift and the faulted phase will be brought closer to ground potential. While a single ground fault may not cause an immediate outage, it creates a dangerous situation. If a second ground fault occurs on a different phase, it creates a phase-to-phase fault through ground, resulting in a high fault current that can damage equipment and pose a significant safety hazard. This is why ground fault detection is crucial for ungrounded systems. A GFR works by continuously monitoring the current flowing in the ground conductor. In a healthy system, there should be no current flowing in the ground conductor because the system is isolated from ground. However, if a ground fault occurs, a small amount of current will start to flow through the ground conductor. The GFR is designed to detect this small current and trip the circuit before a second ground fault can occur, preventing a more serious fault. When selecting a GFR, it is essential to choose one that is specifically designed for ungrounded systems. These GFR typically have a higher sensitivity setting than those used in grounded systems because they need to detect very small ground fault currents. Additionally, it is important to select a GFR with appropriate voltage and current ratings for the system it will be protecting. The installation of a GFR in an ungrounded system involves several key steps. Firstly, the GFR must be installed in the main panel of the mobile lift. This ensures that all ground fault currents are detected before they can spread to other parts of the system. Secondly, the neutral wire from the supply cord should be connected to the neutral or ground terminal of the GFR. This connection allows the GFR to monitor the current flowing in the ground conductor. Thirdly, the ground wire from the supply cord should be connected to the ground terminal of the GFR. This connection provides a path for the ground fault current to flow back to the GFR. Fourthly, the GFR should be set to trip at a current value appropriate for the system. This setting determines how much ground fault current is required to trip the circuit. It is important to consult the manufacturer's instructions to determine the appropriate trip setting for the specific system. Regular testing of the ground fault detection system is crucial to ensure proper operation. This testing should be performed at least annually or more frequently if the system is exposed to harsh conditions. The testing procedure typically involves simulating a ground fault and verifying that the GFR trips the circuit. If the GFR does not trip, it may need to be replaced. In addition to regular testing, the equipment should be inspected periodically to ensure that all connections are tight and secure. Loose connections can create a high resistance path for ground fault currents, which can reduce the effectiveness of the ground fault protection system. It is also important to inspect the equipment for any signs of damage, such as frayed wires or cracked insulation. Damaged equipment should be repaired or replaced immediately to prevent ground faults. Ground resistance monitoring provides another layer of safety by continuously measuring the resistance between the equipment frame and ground. If the resistance exceeds a predetermined value, the monitor triggers an alarm or shuts down the equipment. This can help to detect problems with the grounding system before a ground fault occurs. A Rogowski coil is a flexible current transformer that can be used to measure alternating current without making direct electrical contact with the conductor. It consists of a coil of wire that is wrapped around the conductor. When current flows through the conductor, it creates a magnetic field that induces a voltage in the coil. This voltage is proportional to the current flowing through the conductor. Rogowski coils are often used in ground fault detection systems because they are non-invasive and can be easily installed without interrupting the circuit. They are also very accurate and can measure a wide range of currents. Portable ground fault indicators are handheld devices that can be used to measure the voltage between the equipment frame and ground. This can help to identify ground faults quickly and easily. The indicator typically has a probe that is attached to the equipment frame and a display that shows the voltage reading. If the voltage reading is above a certain threshold, it indicates that there is a ground fault. When using a portable ground fault indicator, it is important to follow the manufacturer's instructions carefully. The indicator should be properly calibrated and should be used in a safe manner. It is also important to wear appropriate personal protective equipment, such as gloves and safety glasses. In summary, ground fault detection is essential for ungrounded 480-volt systems to prevent dangerous electrical faults and protect equipment and personnel. Consider ground fault relays, ground resistance monitors, Rogowski coils, and portable ground fault indicators to ensure a safe and reliable electrical system. Regular testing and maintenance are crucial for the continued effectiveness of the ground fault protection system. By implementing these measures, you can minimize the risk of electrical hazards and ensure the safety of your workplace. Remember that electrical safety is a shared responsibility. Everyone who works with or around electrical equipment should be trained on the hazards of electricity and the proper safety procedures. By working together, we can create a safer work environment for everyone. Additional considerations for ground fault protection include surge protection devices. These devices protect electrical equipment from voltage spikes and surges, which can damage equipment and cause ground faults. Surge protection devices should be installed at the main panel and at individual pieces of equipment. Another important consideration is harmonic filtering. Harmonics are distortions in the electrical waveform that can cause equipment to overheat and malfunction. Harmonic filters can be used to reduce the level of harmonics in the electrical system. Regular infrared scanning of electrical equipment can also help to identify potential problems before they lead to ground faults. Infrared scanning uses a special camera to detect heat signatures. Hot spots on electrical equipment can indicate loose connections, overloaded circuits, or other problems. The National Electrical Code, NEC, provides detailed requirements for ground fault protection. It is important to consult the NEC and other applicable standards when designing and installing a ground fault protection system. Proper grounding and bonding are essential for effective ground fault protection. Grounding provides a lower impedance path for fault currents to flow back to the source. Bonding connects all metal parts of the electrical system together to create a common ground potential. It's also important to verify the integrity of the equipment grounding conductor. This conductor provides the path for fault current to return to the source, tripping the overcurrent protective device. Ensure it is properly sized and connected. Furthermore, consider the impact of variable frequency drives, VFDs, on ground fault protection. VFD can generate harmonics that may interfere with ground fault detection. Special ground fault protection schemes may be needed. When performing maintenance, de-energize the circuit before working on any electrical equipment. Use lockout/tagout procedures to ensure the circuit remains energized while you are working on it. Always use properly insulated tools when working on electrical equipment. Wear appropriate personal protective equipment such as gloves, safety glasses, and arc flash protection. Be aware of the potential for arc flash hazards. Arc flash is a dangerous electrical explosion that can cause serious burns and other injuries. Conduct a thorough arc flash hazard analysis to determine the appropriate level of arc flash protection. Train all employees on arc flash safety procedures. Finally, documentation is important. Keep accurate records of all electrical equipment, including installation dates, maintenance records, and testing results. This information can be helpful in troubleshooting problems and ensuring the continued safety of the electrical system.